you for inviting me here. It's a pleasure to be in Moscow in such a beautiful time of the year, I guess, where the summer and then the weather is nice. So indeed, yeah, I'm going to talk about something maybe a little bit more theoretical than last time, but I didn't want to scare you too much. So it's still about preferential model that you probably recognize. So something that it's used as a model for complex networks, but this time we'll be looking at more classical graph parameters like perfect matchings or Hamiltonian cycles. So this is a joint work with Xavier and Ben. So those are my two postdocs this year. Xavier is, I guess, leaving for US this year, and Benjamin as well, to different places. And Alan Fries is from Carnegie Mellon University. Those are my co-authors on this particular project. So as you know, I'm interested in graph theory, which is a fancy name for networks, but also I like probability. So I try to mix these two things. So of course, you know, how probability can come up into the graph. Well, there are two different ways, I guess. One, maybe you're just looking at a random graph. So you look at the graph which is generated at random. Maybe it's a binomial random graph where things are happening independently. Or maybe you place some vertices on a, say, sphere or on a unit disk, and then you connect them somehow. So we had one example of those spatial graphs before, namely the spatial preferential model. And of course, you know, you can try to look at some graphs that can be used as a models of complex networks. So, for example, maybe you have a preferential attachment model or other things. So that's one way the probability can join graph theory. But of course, that's not the only one. And if you stick with random graphs, you can look at questions like, you know, for example, classical chromatic number or classical matchings or Hamiltonian cycles. So you can do whatever you want with these graphs. People look at deterministic graphs. So for those graph parameters, you can try to you know, investigate what happens in a random graph. And many interesting things are happening, and people study them a lot. But the other way, you know, the probability can come up into the picture is that maybe you have a deterministic graph, but now maybe the process is random, and I like those things as well. So, you know, one example might be, say, rumor spreading or bootstrap percolation that is well studied in the literature as well. So maybe I have a lattice, so it's a, you know, deterministic, very simple graph, and maybe, you know, randomly some points are active. And then you have a very simple deterministic strategy, namely, if you have more neighbors that are, say, active than non-active neighbors, you become active, or any other deterministic rule you can think of. And then, you know, things are, you know, the situation is evolving, and maybe the question you want to ask is, what is the probability that at the end of this process, everyone is active? So that's another way the probability can join the graph theory. And of course, the third way, I guess, you can think of is that you still have deterministic graph, you still have deterministic process, but maybe use probabilistic tools to analyze those things. So that's another possibility. So the outcome is deterministic, but you use heavy machinery from probability to solve your question. So I think all of that is interesting to me. So that's what I do. And today, like you heard, we'll stick with the preferential model, and then I look at some deterministic question. You know, once you fix the graph that is generated at random, I'll be asking, you know, what is the probability that this thing has Hamiltonian cycle, for example, or perfect matching. So that's the story. And as before, as last time, every single property I'm going to talk about is going to be asymptotic. So I'll be always assuming that n, the number of vertices, is tending to infinity. So of course you can try to apply those tricks for you know, finite graphs, but that's harder. So we don't want to estimate, you know, precisely the probability for a given n. All we care about is whether the probability tends to 1 as n goes to infinity or not. So if that is the case, then we say that the given event holds asymptotic almost surely. So again, everything I say today is going to be asymptotic, n tends to infinity, and everything I say will be asymptotically most surely, which means the probability that this happens tends to 1. Right? And that's not kind of like, that's not because I just like it this way. There's no other way, I guess, because, with probability tending to 0, or, with probability 0, some strange things can happen. Like, for example, all the vertices in my spatial preferential attachment graph are placed on the same position. All right, so that's the graph. Well, that's the kind of like a setup I'm going to look at. But what we're trying to find, well, we're trying to find a Hamiltonian cycle, Hamilton cycle. So what is that? This is a cycle that spans all the vertices. So I want to have a cycle so that the cycle goes through every single vertex, and it's of course part of the graph. And then also I want to have a perfect matching. So we want to match vertices 1 to 1, and try to match all of them. So of course, there's no problem with parity for Hamiltonian cycle, right? For Hamilton cycle, because if n is even or n is odd, doesn't really matter. You still have a chance to find it. But with perfect matching, of course, if the number of vertices is odd, you have a problem, right? So no matter how hard you try, you're never going to succeed and match everyone with everyone else. So we do, we relax this, and we are happy with the definition as follows, that they have a perfect matching if it matches floor of n over 2 vertices. So if I have odd number of vertices, then I'm going to be happy with matching that is best possible, that matches all but one vertex. And with Hamilton cycles, of course, I want to have a cycle through every single vertex. Yeah, as always, don't hesitate to ask any questions. If something is not clear, I'm trying to go slowly, so hopefully it makes sense. But yeah, if I miss something, then let me know. I'll try to clarify that. Okay, so you might wonder, why do we care about perfect matchings? Because, if I can show that I have a Hamilton cycle, then clearly I have a perfect matching. So this is a stronger property. But of course, we can think about these things independently, because perhaps it will be easier to get a perfect matching than Hamiltonian cycle. So, you still might want to ask the two questions. And what is the intuition behind? I guess in the random graphs, it's very common that the trivial obstacle is actually the only obstacle. So, for example, if you ask the question, is the graph connected? Then of course, if I have an isolated vertex, then the graph is not connected. But if it happens that there is no isolated vertex, then already at that point, asymptotically most surely, the graph is connected. So that happens with binomial random graph, and this property is true for many other properties in a graph theory. So random graph, in some sense, it's an interesting object, so that very often the trivial bottleneck is the only bottleneck you have. So you might wonder, oh, okay, so what about, say, perfect matchings, or what about Hamilton cycles? Then clearly, of course, if you have an isolated vertex, there is no perfect matching. If there is a vertex of degree 1 or 1 or 0, then you don't have Hamiltonian cycle, right? That's clear. So you might wonder, oh, so if I do not see it, is it the case that the graph has a perfect matching or has a Hamiltonian cycle asymptotically most surely? And that happens, it's true for many random graphs. So the classic binomial random graph, GNP, and then the counterpart GNM, which is the graph on n vertices and precisely m edges that are sprinkled across the whole graph. These two guys have this property. So again, what is the property? Property says the following: if I give you a graph generated at random, all I care about is that whether there's a vertex of degree. What is the minimum degree, right? If the minimum degree is, say, at least 2, then I say, oh, with high probability, it's fine. I do have Hamiltonian cycle. If it's not, then of course, clearly you do not have Hamiltonian cycle. So that's true. This bottleneck is the right one for binomial random graphs. And for example, geometric graphs, Wormald, that was my postdoc supervisor, and Xavier and Tobias, they showed that the same holds for random geometric graphs. So again, the only bottleneck is maybe those isolated vertices or vertices of degree 1 or 0. So as long as you don't have it, then everything is fine. But it's not always the case. There are some exceptions. So for example, if you look at random d-regular graph, so I'm not sure we discussed this model before, but random d-regular graph is a graph on n vertices, taking uniformly at random from all the graphs that are d-regular on n vertices. So the way you can think about it is that I generate all the graphs that are d-regular on n vertices, put them into a big box, and then take one uniformly at random, and that's my object I want to study. And if, say, d is equal to 2, then my random 2 regular graph is, of course, a collection of cycles, and it's not so hard to show that with high probability it's not connected. So you expect log n cycles, log n components, and therefore there is no Hamilton cycle there with high probability. But on the other hand, if d is at least 3, then there's this classic result of Robinson-Wormald that says that you do have a Hamilton cycle. There's of course much stronger properties, but that's known now. So again, this shows that it's not the case that this trivial bottleneck is the real bottleneck, because if d is equal to 2, technically there is a chance for Hamilton cycles, but asymptotically more surely there is not one. So, but 3 already works. Another example where this fails is the M-out graph. So what's M-out graph? I'll discuss this a little bit more in the next slide, because I think this will be a useful model to think about for the preferential attachment. So what's the M-out model? So you pick your favorite M. It could be anything, any natural number, and that's your out degree for now. And you have n vertices. So what's going on is that every single vertex would like to connect to 3 or m in general other neighbors. So what this vertex is doing, this vertex is picking 3 neighbors uniformly at random from all the neighbors. So maybe like that. So you have 3 independent rounds, and each time you pick one guy. Then maybe another vertex tries to do the same, and the distribution is not affected by anything else. So every single vertex independently making a decision where to connect to, and sends exactly m edges, and those neighbors are chosen uniformly at random. So of course, maybe I create a loop, but that's fine. So myself is all, I include myself into the probability distribution, and also you might go to the same place 2 times. So again, you have n independent events, and each event in some sense is m independent events. So you have m times n independent events. You just jump to the random place. And that's your directed graph. And now you forget about edges, and that's your object you want to study. So you will see in a second why it's going to be useful for our discussion. But again, maybe come back to this. It's known that this 2-out graph, and actually even 1-out, could be technically Hamiltonian, right? Because if you connect to one neighbor at random, then after you forget about directions, you have 2 regular graph, or average degree is 2. So technically, there is a chance. But even if the minimum degree is at least 2 in this model, you still rule it out. So even if you pick m equals 2, then the minimum degree is trivially at least 2, but then there is no Hamiltonian cycle. You need 3. And that was actually a long series of papers. It was highly non-trivial. People started with some tower function for m, and then going down, and now we know the whole story. In a very sophisticated paper, and quite recently, Tom Booman and Alan Fries, they showed that that m equals 3 is already enough to have Hamiltonian cycle. But anyway, so 3 is enough, but 2 is not enough. But the minimum degree is 2, so it could be enough, but this idea fails. So usually this trivial bottleneck is the right one, but not in those two cases. Yeah, we've been here. So what about preferential attachment? So now I'm looking at this classical model of complex networks. So it's something that I already discussed like this last time. The last time it was a spatial preferential attachment. Now it's just the old good friend preferential attachment model. So what is the story? Again, similar to before, we have n vertices, and then I have m edges. M can be anything you want, any natural number. And you start from the first vertex, and this vertex picks 3 neighbors and picks himself as a neighbor. So we start always with m loops around the first vertex. And then the second guy tries to connect to somewhere, and then what is the process? Well, the process is as follows. Each edge is kind of try to decide where to go, and it goes to one of the older neighbors, or goes to itself. It could happen too. And it goes with probability proportional to the current degree. So this guy already kind of contributes to its degree. So there is a chance to create a loop, but you know, it's highly likely, at least, well, not highly, I guess it's still a positive probability it happens, but later on it will be less and less likely that we have it. But there are loops in this graph. So then we go to the next edge. So I update all the degrees, and now this edge goes to a random place, and the probability I go to a vertex V is proportional to its current degree that I keep updating every single time. So that's the model. And you know, you just keep going like that, and always, you know, these guys are not introduced yet in the model, but always you connect to vertices that are already there. Right? Does it make sense? It's maybe a little complicated, but that's a classic model, so hopefully you've seen that before. So each time you jump to k places, each time you update the degrees, and then the rule is that you go to vertex I with probability proportional to its degree. So as before, I mentioned that, you know, you have the so-called rich get richer principle. So of course, you know, if you're lucky at the very beginning, you attracted a lot of people, and a lot of people connected to you, then your degree became maybe larger than others, and that of course shapes the future of this process. Namely, you know, when you are rich at the beginning, for some reason, maybe just pure luck, or maybe, you know, you're old and that's why you're rich. So it doesn't really matter, but if you are rich at some point, then the probability of stay rich is of course higher than others. So this is the so-called rich get richer principle, which explains, for example, why the power law degree distribution occurs in these networks. So that's the phenomena that we see here, and indeed it's known now that the degree distribution is following power law. There are, of course, more results on that, extending the ranges and so on. But as the first, I guess, Bolobash, Jordan, Spencer, and Tsunadi, they show that you have this power law degree distribution with exponent 2. So that's why it was kind of considered to be a good starting point for complex networks. And also we know that if m is at least 2, we have the graph is connected. I'll need that at some point. If m is equal to 1, then, as I said, there is a chance for a loop, and then every time I see a loop, that will be a new component. So there's going to be log n components in expectation at the end of this process. No, it doesn't make any sense? Okay, so there were many models, so, you know, I should remember some of them. So preferential attachment model is important. This m out is kind of important too. But not as much as this one, and there's something in the middle. So when we started trying to analyze this model, we thought the following: well, this preferential attachment rule is a little bit technical, but it's not a big deal. I think the main bottleneck we thought is going to be because of you always go to the older guy. It's actually not true, so we were optimistic initially that the other problem is easy to solve. It turned out it's actually not so easy, but you know, at least we kind of have it in 2 steps. So again, this M out and preferential attachment model are very similar, right? But there are 2 differences. If you look at M out, then you go to M neighbors. You connect a vertex with M neighbors, but you take them from anywhere, and you take them uniformly at random. In the preferential attachment model, you start on a vertex. You don't take uniformly at random. You go towards, you know, vertices of high degree. So that's one difference. The first difference. The second difference is that you don't go anywhere. You go always to older. So again, we thought that going to older is the main obstacle. So that's why we defined the following model, which we called, I guess, uniform attachment. I used to call it old, like G old or something like that, but let's call it uniform attachment. So this is something in between M out and the preferential attachment model. So this time, what do? You start with a vertex. You just keep going one by one, and at some point you are generating edges from this vertex. So the same as in the preferential attachment model, you generate M edges going towards older vertices, but this time you're not using the preferential attachment model, you just join uniformly at random 2 places. Right? So that's the only difference, and that's the model I think you want to focus on. So preferential attachment and this uniform attachment. So M out is kind of it's already investigated, so you can forget about it. So just these 2 models. I hope it's not too much to remember. So yeah, that's the probability of going to I is exactly the same as the probability of going to I prime. So this time we don't have rich get richer principle, but I guess we get a little bit like older are slightly richer than younger. But of course, what is the expected degree? The expected degree is the highest for the first guy. But what is the expected degree? It's essentially m over n each time. So you get m log n as the expected degree at the end of this process. So indeed, this guy will have high degree, but only logarithm of n comparing to some polynomial for the preferential attachment model. So that's not a big deal, but still you have slightly, you have slight preference for older guys. Okay, so that's the main result. So you don't really care about those numbers, but we want to have some kind of benchmark how well we're doing. So far the paper is not submitted yet, so these numbers are fluctuating, but I guess those numbers are for today. We show that if m is large enough, whatever it means, then all these models have both perfect matching and Hamiltonian cycles. And again, of course, this implies that, but as you see, there's a smaller number there. So for smaller numbers, we can claim that we have a perfect matching, and then for larger number, we have Hamiltonian cycle and perfect matching at the same time, of course. So those are the main results. And let's see how it goes. So how we started this project? Well, during I think last summer, we had 3 or 4, let me count, Callum, Nick, and Kirill, and Rita. So 1, 2, 3, 4 students came for the summer. They were undergrad students. So we came up with a question for them about vacuum robot that is traveling the graph. So that was a very cute problem for undergraduates. But as a corollary of that work, of course, everything was about different model, different problems. But as an outcome, we got that for m equals 2, this preferential model has no Hamiltonian cycle. So then we thought, well, preferential model is a well-studied model, and Hamiltonian cycles are classical graph parameter, right? So there must be something known about these things, but we couldn't find anything. So it seems like it's not studied yet. So we said, well, let's try to prove something about these guys. So that's how it started. So we're a little bit surprised that it's not known. So what you can do from the lower bound, I'm not going to talk about these things, but you can show that for m equals 2 and then m equals, you know, you don't have not only Hamiltonian cycle, that was kind of like implication of something else that we did in the past, but also you can show with a little bit more work that in fact is universal attachment also doesn't have a Hamilton cycles. So that's what we have. And I think maybe 3 is ruled out for Hamilton cycles as well, but yeah, I'm not sure about it. So probably more is known at this point. But clearly those upper bounds that I claim here, those are probably not the right ones. So I don't see a reason why you need to have, why m has to be 6,000 to have this. It's probably a much smaller number, but it's difficult to get a handle of those things. But I wouldn't be surprised if you know, someone improves it eventually. So why we're optimistic? So I don't want to go into details because it's terrible. So I'm trying to do. Still, some of those parts will be a little technical, but some of the parts are quite hairy. So I'm not going to bore you with those things. But why we're optimistic about the fact that once we know how to do it for universal attachment, you can go to the preferential attachment model. Well, the idea is that all our proofs will be based on the so-called two-round exposure. And the problem is that with preferential attachment model, it's not so easy to define this two-round exposure, and that's a very technical thing. But I think, well, I hope we know how to do it, and that's going to be you know, like 10 pages of the paper. So that's highly non-trivial. But let me focus on uniform attachment then. So everything I'll say today, I guess, will be for this. And then just believe me, switching to preferential attachment is possible using the same tricks, exactly the same tricks. But it's more technical because we don't have such an easy two-round exposure. So let me talk about this round exposure, and then maybe we can briefly talk about preferential attachment. So what's two-round exposure? This is a really cool technique in, say, used in binomial random graphs. So the idea is that if you want to, say, generate a graph G and P, where P is equal to half, you can first generate a graph P with P equals 1/4. So you have this graph like that, and then you sprinkle extra edges. So with those versus those pairs that are not connected yet, you put them with some probability. It's not half, of course, but you tune your parameter somehow, so that at the end of this process you connect two pairs with probability P. So you start with your sparser random graph, and then on top of that you sprinkle some random edges, and at the end what you're getting is the desired random graph you want to study. But the beauty of that two-round exposure is that, you know, you can stop after one round, measure what you have, and then perhaps the sprinkling extra edges are going to help you to achieve your goal. So that's a very important, very interesting trick. And maybe for this model, it's actually even easier to understand. So let's say my goal is to analyze what's going on in the uniform attachment model for some given m. So m is maybe 10. So what can you do? You can generate a graph with 5 edges, with m equals 5, say m1 is 5, and then m2 is 5, and then you do it independently, and then you put 2 copies of the same graph together, and I claim that what you are getting at the end is m equals 10 graph. And that's easy to see, right? Because again, how the process goes, at each time of the process, I look at the vertex, and then I generate m edges. That's the original UA and M. So I generate m edges. But no one can stop me with, say, coloring the first m1 of them blue and the last m2 red. And then, since things are happening independently, what's happening with blue does not affect red, and vice versa. So the graph with red edges is just simply U and M1. And the graph with red edges is simply, independent graph U and M2. So you can, I can say, Andre, generate this graph. I generated at home this graph. We exchange notes. We come up, together, put these two copies, and then give it to someone and say, look, this is UN M1 plus M2, and that's perfectly fine. So that's a very simple trick, but very importantly, you can just stop at this, this process, do something clever, and then sprinkle extra edges, and finish the job. Yeah, no questions, no comments. So unfortunately for preferential attachment model, it's way more complicated, but we have a way to deal with that, which is it's interesting by itself, but that will be another 1 hour and 30-minute talk if I want to do it. So just believe me, it's doable, and let's stick with this model. So after the first round, yeah, I picked my favorite M1, and then I want to stop at that point, and I want to look at the graph and what the graph, how the graph looks like. I claim that the graph has nice expansion property. So what do I mean by that? Well, I mean that every small set, which has size at most 2 epsilon n, every small set expands well. So what does it mean? Well, it means that if I look at the neighbors of neighbors outside of that set, then I have 2 times more neighbors than I start with. So regardless which set you give me, maybe it's just 1 vertex, maybe it's 13, or maybe it's 1% of the graph. I don't care how large set you give me, and every single graph, every single set has to have this property. The number of neighbors outside must be large, must be at least 2 times bigger than the set itself. So of course, epsilon is some constant, which is a function of M1. So I'm skipping all those technicalities, but that's the idea. So I want to show that the graph generated by this uniform attachment, and the same will apply to preferential attachment model, this graph expands well. And also, I'm going to show you that at that point, there's a long path in this graph. So those 2 things, and that's all we need to have at that point. And also the important but trivial observation is that, of course, these 2 properties will stay true if I keep adding edges. Because remember, I'm going to sprinkle extra edges here and there. So if I keep sprinkling, guys, I don't want to destroy these 2 properties. But of course I want. If at the beginning my graph has these 2 properties, if I keep adding edges, regardless where I do it, where I put them, still the expansion works, and the length maybe the longest path maybe is increasing, but definitely is not going to decrease. Okay, so that's the first round. So this is a big picture. I'll come back to that in a second. What is the second round? So this is sprinkling. So I start with this graph after the first phase and keep sprinkling, keep adding some edges. So we generate a sequence of graphs, and every new graph has extra edges. So the earlier graph is a subgraph of the next one. So I keep adding edges, and I'll do it in a smart way. And each time I'm hoping that the next graph is better than the previous one. Of course, I cannot guarantee it, but I hope it's going to be better, very often. So what do I mean better? Well, it means that the length of the longest path is actually bigger than it used to be. So I'm hoping that the sprinkling is helping me, so my path is increasing and increasing. And of course, if it increases up to n-1, there's no way to, or n, there's no way I can increase this anymore. So I hope that at some point, I'm getting a Hamiltonian cycle. So that will be my kind of like, I will be happy. So I'll be doing this sprinkling, and I will be happy and jumping up and down when the path increases, or I get a Hamiltonian cycle, because then I can go home and be happy, right? So that's what I mean by improves. And my goal will be to convince you that the probability I improve is at least 3/4. So I cannot guarantee to be happy, but with probability at least 3/4, I'm going to be happy in every single step. So of course, if you wait long enough, and we can wait long enough because we have enough edges to sprinkle, if I can wait long enough, then we win, because I'll be happy, very often using just the Chernoff bound or whatever you want to use. So I have to be happy enough time to win the whole game. So those are two phases. So I'll be going through them carefully. Well, some things are, of course, omitting because it's going to be too technical, but I'll just focus on nice ideas and easy to follow, I hope. So yeah, first of all, we want to show this expansion property. So again, what do I mean by the neighbors of S? I want to look at all the neighbors, all the vertices that have at least one neighbor in S, but they're outside of S. And this is one of the technical lemmas that I'm going to skip because that's just hard work. You just have to sit down and do it with a piece of paper for 10 pages. But the idea is that you pick your favorite alpha, then you select your M large enough so that then you get the expansion you want. So you have two for Hamiltonian cycles, and one is needed for matchings. But as I said, I'm going to focus on Hamiltonian cycles. But either way, of course, this M is a function of alpha and this 2 or 1. So, for 2, of course, I need to go for larger M. With 1, I'll be happy with smaller M. So that's why we see those differences in the result, because I can make this lemma, technical lemma, to be true for smaller value of M if I'm happy with 1 instead of 2 here. So this is this expansion, but that's ugly. So I'm skipping. So let me look at some easy stuff. And the second one is actually quite interesting, and I already used this a few times in the past. One of them, it was used to get a simple proof for size Ramsey numbers that beats much, by a lot some other existing proofs. So that's kind of nice technique, but very simple one. So, but this one is obvious, I guess. So what we want to show that first, every set which is large enough must have some edges. So those are the properties of my graph. And the second thing I want to show is that if you give me two large sets, then there must be some edges in between. So I need that property. And this property is actually very simple to do because it's all you need to do is the so-called first moment method. So you want to show that the expected number of such situations is tending to 0. And if that's the case, that means that asymptotically more surely it's never happening. So yeah, so we just pick, you just go over all sets of that size, look at what is the probability that this set induces empty set, and then you do calculations, and that's not too complicated, and you show that it's tending to 0. So we have this lemma, and then, like I said, the nice application of that is that, especially for the second one, we get something interesting. But the first one is quite obvious, because if every single large set must have some edges, that implies that there is a large matching. Right? Of course, we cannot guarantee to have a perfect matching, but definitely there is a large matching. Right? Can you see that? Or it's too late to see it? So how can I construct the matching, right? Let me say a few words. It's easy, so you should wake up if it's not following. That's another good sign. So I want to construct a perfect matching. So what do? I create this perfect matching gridly. So start with your favorite edge, and then next edge, next edge, next edge, next edge. So if you get stuck, then what does it mean? It means that the set that you're looking at is independent. There's no edge there. So if the matching does not cover all vertices, it covers only some number of vertices, but epsilon fraction of them, then there must be a large independent set. So if you don't have a large independent set, there must be a large matching. So that's easy. And the second one is nice. So that's the trick I like. That's maybe because I came up with this and it's proved to be very useful and solved many conjectures and improved many bounds. So the trick is very simple and nice. So what do you do is the following algorithm, if you like algorithms. So you start with your graph, you put every single vertex in set B. So what do you do now? Pick your favorite vertex, put on the left. Now investigate all the connections between this vertex and this set B. So if you have an edge there, you maybe have 3 edges, then pick your favorite vertex and put it on the left side. And then keep doing. So again, I'm investigating all the neighbors, all the connections between this guy now and this set. And if I see some neighbor, just put it on the left. So keep going like that, and of course at some point probably you're going to stack. So what does it mean then? Well, it means that there is no edge between this vertex and this set. So what can I do now? Take that one and put it in C. So you put it in C, and path is a little bit shorter, and you continue the process as before. But what is the more important, what is the most important observation here? Well, clearly there is no edge between C and B, right? Because that's how I, do the algorithm. I always put a vertex from here to C if there is no edge from here to B. So there is never an edge from C to B. And the second observation is that each time I either take a vertex from B, put it there, or take a vertex from here and put it C. So either size of B goes down by 1 or size of C goes by 1 up. So at some point, I'm going to get exactly the same number of vertices in B as I have in C. So what is then the conclusion? The conclusion is that if I have my graph, the graph can be partitioned into a path and 2 sets of the same size with no edge in between. Oh wait, but now you say, well, but now I have the property for my graph that 2 large sets, right? 2 large sets must have an edge in between. So they're not large. They must be small. And therefore, there is a long path. So, I don't know. I guess I'm getting old. I like easy proofs now. Like it's fun to do like 20-page long proofs, but this is very cute. And like I said, this was used, for example, to go down with size Ramsey numbers, the problem of polar dash. So the bound of, say, Bela-Bolobash goes down from 740 to 74 or something like that. So this is kind of a cute application. So yeah, so that's it. So we have again, if I look at my graph after phase 1, I have a large matching if I care about matchings, or I have a long path if I care about Hamiltonian cycles. Okay, so now what did we prove? Yeah, we have this expansion, which I didn't prove, but I hope you believe me, it's true. And then we have a long path. So now I think it's time to think about the second round. So I start sprinkling, well, not yet, but I'll start sprinkling soon. And the question is, how can we keep extending my path until I'm lucky and I have a Hamilton cycles. So I have the following definition. So if I give you a graph G at any point of the process, I will be recalculating these things all over again. Every single time I sprinkle a little bit of vertices, I'll recalculate that A and then BV again. So I'll be doing this many times. So what's A? So suppose that I look at all the longest paths. Maybe there's just one, or maybe there are a million. I don't care. Look at all longest paths And then set A is the set of all endpoints of some paths. So I hope it makes sense. And then if I give you one endpoint of a path, I want to look at BV, which is the set of all possible endpoints of paths that start at V. So I start at V. I want to have I want to look at the longest path from that vertex. Maybe again, maybe have just one path. I'm guaranteed to have one because V is in A, but maybe there are a million paths that starts at V at our longest. So maybe my BV has many vertices, but that's fine. And then I have the following simple observation that if G is connected, that's important, so that's why we kind of have to prove it or have to use the Bolobash result that says that the preferential attachment is connected, or the uniform distribution is connected. And then I have the following property. So if we add an edge between some V, I don't care which one, so pick your favorite V from A, and then you connect this to any vertex from BV, then I claim that we increase the path or finish the job and have a Hamiltonian cycle. So how is that possible? Well, that's again easy observation. Look at path. That's the longest path in your graph, and V is the end, the beginning of the path. W is the end of the path, and now I add an edge between those two guys. Of course, if this path is a Hamiltonian path, I'm finishing the job. It's Hamiltonian cycle. But if it's not, then it means I have some vertices here in this potato, right? They're not part of the path. But now what? Well, the graph is connected. So there must be an edge from one of these guys to this potato. But now, of course, I have a path that is longer. So, very simple observation. Okay, now maybe it's slightly less simple. So I'm not sure you heard about Poiseuille's rotations. So here's a very interesting trick that works beautifully for random graphs. So suppose I give you path P. It doesn't have to be longest, but of course I'll be looking at longest paths. So I give you any path P, and the beginning of that path is A. So what can be done with this path? Well, I can keep rotating that path. So what does it mean? It means that I can transfer from P to P prime as follows. If there is some edge from the endpoint to middle of the path, instead of taking the original path P, I can do the following, can jump, use that edge, and go backwards. So that's the rotation. So if I give you a path P, pick your favorite edge and do your rotation, that's going to be a next path that is obtained from that rotation. It's great. So what do I mean by this set and PA? That's the set of all possible endpoints, of all possible paths that can be obtained after rotations, but not only one rotation, maybe have a sequence of many rotations. So you can do as many rotations as you wish. If you start from path P, and the root A at the beginning of the path is A, so you start that and you keep rotating as many as you wish, and then of course you're discovering different edges. Like this point, of course, will belong, this vertex will belong to that set, but maybe that's not the only one. Maybe there will be plenty of others. So I do any sequence of rotations, and those endpoints are going to be all in the set. Does it make sense? That's kind of important, so I'll prefer to make sure. Okay, so then what can we show? Well, we can show, and that's again not that complicated, or that's what Posh, I guess, shows, is that if you look at the expansion of that set, it does not expand so well. So if we look at the neighbors of this endpoint set, then the neighbors are going to be, the size of the neighborhood is smaller than 2 times this set I started with. So I cannot control how large this set is, but does not expect well. It does not expand well. And this time I have to assume it's longest. So the definition doesn't have to be for a longest path, but now I have a longest path. And if it give me any path you want, and any endpoint of that path, all the rotations you can think of, then all endpoints, they do not expand well. So I can probably even try to prove it quickly. So how does it work? Well, first of all, there cannot be any neighbor of any endpoint outside of the path. Why not? Well, if that would be the case, then you could extend the path, but it's not possible because that path is actually the longest. So that would contradict the fact that it's the longest possible. So all the neighbors of endpoints are on the path. And now I think this might be more complicated, and I don't have a whiteboard. But I guess if you have a path, and then you look at the vertex, you look at the vertex that is a neighbor of some endpoint, then it must have some also endpoint attached to on the path. Because otherwise, again, you could just extend the path. So then what does it mean? It means that you can just count instead of, so these edges across the path, they're not helping you. So if you're here, if you're endpoint, then you have maybe a neighbor on the left, maybe a neighbor on the right, but then all your neighbors somewhere else, you can forget about them. You don't have to count them because they will have some other endpoint nearby. So you simply can count neighbors around you. But of course, you can have at most 2 of them, and the initial point A has only 1. So the number of the size of the neighborhood is at most 2 times the neighbors itself minus 1. So that's a known observation. But what's now interesting is that, well, what did we prove? So look, here we proved that the set of endpoints is not expanding well. But we know in our graph, every small set expands well. So endpoints do not expand well, but every small set expands well, which means endpoints are not small. So that's great, right? So endpoints are not small, so I think we can try to start thinking about the second round. Because again, every time I be sprinkling edges, I'll be recalculating A, we'll be recalculating B. But again, I know by this lemma, if I have a longest path, then my endpoints cannot expand well, but every small set expands well, which means endpoints are always large. So yeah, so I'm going to show, and I think probably that doesn't require proof, but we can contemplate on that a little bit. So the set A, every single time I keep sprinkling, my set A is large. And no matter which vertex you pick from A, then this BV, the number of endpoints of V, is also large. And again, why is that the case? Well, let P be the longest path. I don't care which one you pick. And pick V as a endpoint. We know from the lemma, deterministic lemma, right? We know that the endpoints are not expanding well. So that's what we know deterministically. But we know that our random graph, every small set expands well, so the set of endpoints is large. And that's why, A is large. So again, let me come back to this. This is true if we keep sprinkling. So I have this property for M1, for the graph that I get at the end of the first phase. So I have this property, and I keep sprinkling, but of course sprinkling only helps. So, and regardless which time I'm looking at, regardless what is the graph I'm looking at, this graph has this property. that I keep recalculating A, so A keeps changing each time, B's are changing each time, but I don't care which time I look at. Every single time I have large A and large B for every A. And you let me recall you one more thing, this observation that we have very simple. Every time I add V and add an edge between V and someone in BV, then I improve my situation. So now I hope you see what's going on. In the binomial random graphs, we are kind of very lucky because things are, in the second round, things occur independently. So the sprinkling just does the job very easily because, there's a high chance that the random edge will connect vertex V and W. But here, we have to work a little bit harder, but the same idea. We'll keep sprinkling and keep improving our situation. Okay, so let's recall, I think I said most of this, or not, if not all. So we started already with M1, right? We have good expansion, we have good A, large B, everything is nice, and I just keep sprinkling with extra edges. These edges will come from M2, right? So this extra edges coming from completely independent copy of M2. So that is not affected by blue. So those are my red edges. So again, each time I keep updating A and all the B's. And then, of course, how can we use my second round exposure? How can we use those extra edges? Well, since those extra edges are coming from this graph, I can take a vertex and ask, who are your neighbors in the red graph? But of course, once I ask you that question, when I ask that question to a particular vertex, it's gone, right? I expose that information, I know those edges, so I cannot ask this guy again, right? But if I ask someone else, then the answer is revealed to me and I can predict what's happening. But I cannot ask twice the same question to the same person because, I revealed that extra information about red graph. So we cannot ask the same question to the same person. So what do I do each time? I just pick the youngest guy that was not asked yet. So I pick the youngest unmarked vertex from A, and I mark it. So again, unmarked means I never ask this question to this guy. So I pick the youngest. Why the youngest? Because I want to have a lot of older guys still available to connect to. So that's why I want the youngest. You will see a picture in a second. But the important thing is that I have to make sure that I'm asking someone for the first time. I cannot ask the second time. And then I ask that vertex V, who are your neighbors in this new graph? So I sprinkle random edges just from one vertex to outside. And of course, is the property of the model, I'm asking all the vertices. And then that information is revealed to me, and I add this to my graph. And again, I'm recalling this for the next, for a second time or third time. If I happen to be lucky and V connects to BV, then I improve my situation. So here's the picture. Maybe at some point I asked these 4 guys already. So these guys were asked before, and then I know their red edges, so I cannot ask them again. But I recalculate A, and then let's say that's the youngest unmarked vertex. So I pick that, and now for that vertex, where's my B? Well, my B is somewhere here, and the important thing is, of course, it could be somewhere on this side, but not too many verses will be on this side because I jump to the youngest. So all of these verses in this green area, all of those guys are also in A, of course, right? Because A is the set of all the endpoints. So if those are the endpoints of the path that starts at V, that's also endpoints of some path. So these guys are in A. So if someone is green, if someone is in BV on the right side, it could be, but since I jump to the youngest guy, there are not too many on the right. So I generate those edges, and what is the probability I improve? Well, that's this, this at least that. And of course, as you see now, I'm picking M2 to be sufficiently large so that, you know, this is at most a quarter, so I get a good chance to improve. Yeah, makes sense. I think I'm coming to the end. Yeah, that's the end. So it's not expected. I did that presentation a long time ago, so it's interesting to me because I don't know what's coming. But it's a little surprise to me. I should have watched those numbers, but I hope it's okay. It's a little bit earlier, but it's a heavier topic, so I think I'll stop here and I can, you know, discuss anything else you want me to discuss. But I hope you get a flavor of what's going on. So like I mentioned before, this is just for universal attachment model. So of course, one thing to change is how can we move from universal attachment to the preferential attachment. So one thing is, again, one difference is that I'm jumping to verses not uniformly random. I'm jumping to verses with probability that is proportional to degree. But here, look, what we need. So if this guy has high degree, then of course, with a higher chance, I'm jumping to that guy. Right? And since I want to look at what is the probability I'm not picking sums, that's bad event for me, right? I'm worried that I generate those M2 edges, and the probability I do not hit anyone in green, that's bad. But the probability I do not see anyone in green, it's actually nicer for me if these guys are heavy, if these guys, you know, have a large degree, and I'm looking at the preferential model. On the other hand, the only difference will be what? I guess if you think about uniform attachment, you connect to the given vertex with probability 1 divided by n, right? Or t if you think about old guys. So 1 over n, whereas in the preferential attachment model, it's at least 1 divided by 2m. So that's why we were kind of maybe too optimistic at the beginning. We said, well, if we can deal with this uniform attachment model, then all I need to do is stick 2 into my proofs, and everything will be working the same way for preferential attachment model. And it's almost true, right? So that's why, you know, for example, you see, so that's why I think if you look at the statement of the theorem, yeah, you see, I'm not sure you've seen that, but this is twice that, or a little bit more, right, or less. This is twice that. So you know, that's what's happening. We just have to multiply things by 2. But we didn't expect. I don't know, it was silly us, I guess. We thought that this double round exposure is easy for preferential attachment, but it's not. So maybe let me mention that, because I think that's interesting by itself. And that actually might have more applications than anything else we do here. So we can try to use it in anything you want to do with preferential attachment model. But the idea is, again, that if you look at universal attachment, then clearly you can have this sprinkling, right? You have a vertex, and then you can have half of the edges red, half of the edges blue, and think about these things independently. But here, you know, if I ask Andre again, generate preferential attachment model with m equals 100, and I'll generate at home independently with m equals 50, we cannot simply put these guys together and claim it's preferential attachment with m 150, right? Because, for example, right, if Andre, for some reason, is lucky at home and one of his vertex is rich, right? So one vertex is a very rich, very heavy in a red graph. Then I was doing things independently, so I didn't care about that vertex. But really, in the real sum model, you know, the fact that there's a rich red graph, strange red graph, affects the generation of the blue graph, right? So we have to work much harder to have this sprinkling, and you have to avoid some vertices. You cannot sprinkle from there, but hopefully, not hopefully, but fortunately, in our application, we do not have to sprinkle from every vertex. So you can say, I'm happy if 1% of my graph is kind of say, oh, those vertices are bad in the red graph. You cannot generate new edges from that vertex. That's okay. I can still sprinkle from somewhere else. And that's enough for my application. But if you have some application like that in mind, then you can try to use it. It's kind of a very powerful method, but it's technical in the sense that you cannot think about simply union of two preferential attachment model and treat it as a preferential attachment model. You can do it for GNP, you can do it for this universal model, you can use this for M-out model, whatever you want. Random Dirichlet graphs are a little bit more complicated, but still we know there are some results that, for example, you can generate, I guess, two random graphs and then put them together in some sense. It's a little bit slightly more complicated. But you can still do those kind of two-round exposures there, but not in a trivial way in this preferential model. But we somehow, hopefully, overcame this problem. So yeah, now I can stop, I think, a little bit longer, so I feel not so bad finishing earlier. So thank you.
Thank you for your talk. Could you repeat how you get M value from M2 value? So is it true that we, on the last slide, we got a formula for M2 value by given epsilon, but how we make a jump to get this 158 number?
Yeah, so, but you talk about preferential attachment model or the uniform? Uniform, okay. So uniform, it's easier, so let's see. So again, so let's say I generate a uniform attachment model with parameter m, whatever, m say 100. So each time a vertex generates m edges, and each edge is kind of generated independently of anything else you can think of. Every single edge goes to a random vertex from picked uniformly random from all the vertices. So this edge is going to random guy, this edge is going to random guy, this edge is going to random guy. And this process is not affected by the history of this process, it not affects anything in the future. So in some sense I have, like I said, m times n independent events for a given vertex and for a given edge. I just look at one location from a random and then that's where I go to. And now, what about, say, this was m equals 100. What about m equals 50 and there's another m equals 50? Well, here in this process, I can simply color these edges blue. So I do some kind of a coupling. So I color these edges blue. And then if I just restrict myself to the blue graph, I simply have this model. This again, what is the difference if you think about UN M50? Then the whole process goes exactly the same, right? So the idea is that things are happening independently, regardless of anything happening this time. So I have this n times n process. N times m events. And every single event is completely independent on anything else, right? So what I can do is I can ask Andrei to go to his home and do half of those events, and ask you to go to your home and do half of those events. And then, of course, nothing is changing, right? So those are independent events. So you come to me with a blue graph. That's what you get from your part for your homework, and he comes with a different graph, the red graph, and then I can put this together, and that's the same graph. Yeah, we can talk about it later, I guess, but.
So there's no. So you just tried this process for 158. So it wasn't got as a result of some optimization
No, no, it's not. It's only used as a trick. Yeah. So this is a trivial observation, but the beauty of that. So the 2 round exposures there's not even proof or anything like that. So it's just a trivial observation that you can think about this as a union of these 2 guys, right? So that's just the observation. But the beauty is that it's nothing complicated here. But the beauty is that you can just do the blue graph first. Forget about red. Do the blue graph first. And now you show some interesting properties for this blue graph. Namely, you show expansion, you show that you have already a long path, and so on and so on. So you have already nice properties of the blue graph. And now you use red for the sprinkling. So that's the beauty of that approach. But the approach itself, the observation is obvious. Like kind of how you use it is interesting and tricky.
I think the question was about like the final number. So finally you get like 159, and this means, so how you found this M1 and M2 in your particular
I see.
problem, I think.
Aha, I see. So I missed the question, sorry. Yeah, so then, I don't know if you can see it, but of course, I was not careful here in the talk with adjusting constants. So for example, here, if you want to have small epsilon, you need to take large M and so on. So yeah, at the end of the process, you have the optimization process. And of course, since we don't care, at the end of the day, all I need to tell you is that, oh, look, for this M, I have that epsilon and everything works beautifully. So we did optimize things numerically. And there's no point to try to do it, properly. So we just optimize these things numerically, and that number that pops up. Yeah, sorry, I missed that question.
More questions?
Some remarks. This is maybe very useful for automatic theorem proving and self-learning. Then choose a strategy in graph of statement. This is useful. This is valued of Hamilton cycle. Mm-hmm. So Hamilton cycle as part of deduction.
Mm-hmm. Yeah, I'm sure Hamiltonian cycles occur in many different situations, and maybe that's one of them. But yeah, I'm not sure how it's related to that. But yeah, Hamiltonian cycles are like the same applies to perfect matchings, right? Those are the classical graph parameters that occur in the real life and the real applications very often.
Some application.
Yeah. Oh, you want to hear some applications, or? Yeah, there's one application. That's a remark.
One application from many.
Right.
Many.
Yeah. I see. Yeah, it's a classical. It's not that I know a lot about those things, but I can imagine even like simple traveling self is not a problem, right? You want to visit every city and do it in a fast way. Of course, that's a weighted graph, but yeah, there are many applications of Hamilton cycles.
And arrow will be interpreted as inductive step.
Okay.
Some induction.
Okay. Yeah, I can see that. Yeah, I guess more questions there.
Okay. Do you know something about the lower bounds? So you showed that for m equals 2, there isn't.
Yeah. So
no cycle.
I don't know if I have it right. So again, 2 is ruled out even by looking at this funny robot that we're looking at. So Hamilton cycles rule out there. And then we also rule out perfect matchings. It was probably more complicated for m equals 2. So that was a little surprising, but that's it. That's what we managed to do, I think. So yeah, that was already hard work, and I wouldn't be surprised if then we tried these crazy numbers and the answer is 3. That would be more natural than 6,400. But it's also kind of not that surprising maybe, because even if this M out model, people were starting with even crazier numbers and going down slowly in a series of papers, and then even like there was like two out, two in, or one out, two in papers. So so people were trying to squeeze this to the limit, and finally we now know where's the paper? No, we now know the answer. Oh yeah, so this Bowman and Fries paper solves the question. So M3 works, but not 2. But that was hard, and this should be even harder. So Alan is one of the co-authors, I guess. Yeah, there's definitely not a straightforward jump from here to there. So that's just a different level of difficulty. But definitely, someone should work on the lower bounds. On the other hand, we didn't try to push it too hard, because it's probably easier to believe 3 is the answer than 3 is not the answer.
Okay, no more questions or comments. Let us thank Pawel once again for both lectures.
Thank you.